Okay. Okay, great. Recording is in progress. All right. So we're at a good point at 6:30. I'll just introduce myself again. I'm Karen Kinard. I teach a number of the sections of statistics here at this college, and Professor Washington designed most of these slides. I've added to them. So we have a really nice review for you tonight. As you have questions, feel free to type those into the chat box, and either Jonathan Petit from the Learning Commons or myself will answer those in good time as we're able. All right, here we go. So our first unit is on correlation and regression analysis. And we want to take a look at relationships between two numeric variables. And here's a picture of a scatter plot comparing literacy rate to total births per woman. So this is kind of interesting. And it looks like there is a trend here. What we study in this chapter is, does there at least look like there's a pattern at all? Does it look like a strong or moderate or a weak pattern? What does the shape of the pattern look like in terms of all the things you've learned from algebra through the years, like a line or a parabola or a curve that could be a log or exponential, just all kinds of things. We look at shape. We look if anything stands out like an outlier. So we look for all of these things: trend, shape, strength, and outliers. More specifically, there is a coefficient we call R, the correlation coefficient, that only makes sense when there looks like there is a linear association. And when it does look like there is a linear association, this number can give you an indication of how strong direction the relationship is. If R comes out close to +1, then there's a strong positive linear association. If R is close to -1, there's a strong negative linear association. And if R is close to 0, there is no association, or it's very weak. And so again, remember, there's got to first be some linearity there that's obvious for this number to make sense and be useful to us. All right, so here's one for you guys. Play along in the chat box if this is fun for you to do. Which of the following depicts the strongest positive correlation, A, B, C, or D? Oh, look at them chiming in fast. Lots of consensus, and you are correct. D. D. Because the points are tightly packed together and there's a lot of density moving from lower left to upper right, there's a positive relationship. It does look like this forms kind of a very thick line, but there's a linear association nonetheless. Very good. All right. We want to be sure to remind you that association between two numeric variables is not sufficient evidence to conclude that there's a cause and effect relationship. In statistics, we study cause and effect relationships through carefully structured experiments, well-designed experiments that rule out maybe other variables that could fake us out and make us think one thing's causing another, where all along there's some other variable lurking around that hasn't been accounted for and hasn't been teased out of the control versus the experimental group. So we want to be careful not to confuse correlation with cause and effect. Okay. Here's another example. Let's suppose X is ice cream sales and Y is drowning incidents. We got spring break coming up. Hope everybody have a good time and be safe. But if the correlation is strong, you might think that buying and eating more ice cream causes drowning, because the scatter plot might make it look like there's a strong relationship there. Not so. Probably there's another variable not mentioned that affects both of these variables. One example of that would be temperature. Higher temperatures are associated with more ice cream sales and more swimming. So if there's more swimming, there's more opportunity for more drowning incidents. Just because the two things occur together, it doesn't mean that one's causing the other. Again, we need to conduct a well-designed controlled experiment to make cause and effect conclusions. So don't go looking at a scatter plot and making any cause and effect conclusions based on that. Okay. All right. So what can we conclude from the fact that In this example, the number of liquor stores in a neighborhood is positively correlated with the crime rate in that neighborhood. We got number of liquor stores positively correlated with crime rate. So here's a new question for you all. Let me read all the answers. Is it A, closing liquor stores will decrease crime? Is it B, more liquor stores causes more crime? Is it C, adding a liquor store will increase crime? Or D, neighborhoods with higher than average number of liquor stores typically, but not always, have a higher than average crime rate? A, B, C, or D in the chat box. Ah, here comes another round of letter D. And again, you are correct. You are correct. We stay away from those cause and effect. Conclude. Very good. All right. The basic form of the best fitting line through a set of XY ordered pair points is y equals a plus bx. This is a little different from how you learn to write it in algebra. Nonetheless, it's the same kind of model, okay? The coefficient that stands alone, the constant, that's the y-intercept. That's where the line crosses the vertical axis, the y-axis. The coefficient on the x term is the slope. In this case, b is the slope and a is the y-intercept, okay? Sometimes we put the word predicted in front of the y variable, or we put a hat on the y. Okay, sometimes we do that. All right. Here's an example I want you to think about just a little bit, and then I'll pop in with some answers as we go. Take a good look at this scatter plot with the least squares regression line, the best fitting line, fit through those points. Got a lot of information there. We've got a model at the top that says weight equals negative 266.5 plus 6.138x, or height times height. We see height is the x variable along the x-axis. We see weight is the y variable along the y-axis. So we're using height to help explain weight. Okay. So the first task I'm asking here is for you to interpret the slope. Remember, the definition of slope is that as x increases by 1 unit, y is predicted to increase or decrease by the amount of the slope. Take just a minute and see, if somebody asked you to do this, if you could put that into words in a sentence. Okay, take about 20 seconds here and jot something down. Check in with your answer here in just a moment. All right, welcome to all those who've shown up. Don't be shy. Type answers or questions in the chat box. Right now, I want to see if you can interpret the slope that's given here for this regression line. As x increases by 1 unit, y is predicted to increase or decrease by the slope. So find the slope, consider the variables height and weight, see if you can write a sentence. All right, here comes. As height increases by 1 inch, weight is predicted to increase by 6.138 pounds. Give me a thumbs up in the chat box if you got that right. If you didn't get it right, feel free to type in, ask me a question. All I'm doing is substituting in what x stands for, which is height, what y stands for, which is weight. You're putting in the amount of the slope. Any thumbs ups? Who got it? Yeah. You know, depending on your teacher, you might be answering multiple choice questions. You might be writing some answers, but I'll tell you what, when you're studying, if you can write them yourself, that's even better practice than just looking and picking an answer among the answers. How is slope pounds and not height? All right, hi, Deetra. Let's see. How is the slope is the slope is the rate of change between the two variables. So we actually talk about both the variables as we talk about it. Slope is rise over run. Remember from algebra. And so so it's like rise is how much weight. That's y changes for every unit in increase in x, which is height. So every time height goes up by 1, we predict weight to go up by 6.38 pounds because weight is the y variable. Don't know if I said that right for you in a way that helps. Let me pull my scratch pad over here for just a minute and type you something. Slope equals rise over run, which equals 138 over 1, which equals change in y over change in x, which equals change in weight, which is pounds, over change in height, which is, I think, in inches. Deidre, does that address your question when you see it laid out that way? Wonderful. Take a screenshot of that if you would. Sure thing. Maybe it helps some others as well. So thanks for asking. Take a screenshot of that if you want, please. It'll be part of the recording, but you might want it handy because I've got to move that away for a minute. All right, got to move it away to keep moving on here. It'll be part of the recording. All right. The next thing to consider is whether or not the y-intercept makes sense. Remember that the y-intercept is the predicted value when x equals 0. It's where the line crosses the y-axis. It's the y value, the predicted y value when x equals 0. Take a minute and see would it make sense. You can tell me in the chat box. When x equals 0 and x stands for height, if we had somebody who's 0 inches tall, would it make sense to discuss their weight? Yes or no? You are correct. If somebody is 0 inches tall, I guess they don't exist. There would be no weight. It makes no sense to discuss it. So sometimes the y-intercept will not make sense to interpret. And I think you've seen some examples of that in your homework. All right, very good. All right. On this next one, I'm going to open up StatCrunch and do an example with you. If you want to screenshot this, we're going to get the least squares line for this data. We're going to describe the shape, the trend, and the form of the relationship on the scatter plot. We'll interpret the slope, and we'll interpret R and R squared, and then we'll make a prediction. I mean, these are just like all the kinds of things that we do in chapter 4. So this is really kind of a, let's put it all together now, kind of question here for you. Let me see if I can make StatCrunch small enough. Wrong file. Oh, I had it open. Give me a sec. If you're not using StatCrunch yet, you might enjoy getting to know it. And I'm going to demonstrate doing this correlation and regression here. This is X is going to be hours spent on an essay, and Y is going to be grade. And this is inside my stat lab. I tell my students, especially, and I don't know how other teachers have their HonorLock set up for remote testing, but if you're doing HonorLock remote testing, you very likely will need to press live support inside HonorLock and ask them to help you open StatCrunch. My students, I have I have Honor Lock alerted to do that for you. So you just go to live support and they'll do it. Let me get this data entered. I'll show you how easy it is in StatCrunch. Okay, for anybody using the graphing calculator, if you go to YouTube and do a search on Ross Brooks calculator videos or Karen Kinard calculator videos, you'll get, look for my playlist, and you'll get a very nice list of videos to help you review using the graphing calculator TI-84 to do this work. We've kind of moved away from that in some of our classes, so I'm going to present StatCrunch tonight, but I can tell you, just go to YouTube and look up Karen Kinard calculator and playlist, and you get them kind of in the order of the topics as they come along in the course. And that ought to be very helpful as well. Hopefully I've gotten those in correctly. All right, so watch now, play again later. But what's important is that you put the X and the Y each in a column. And then if you go to Stat, pull down menu, and go all the way down to where it says regression. And John, you're in my class. You will be able to use your calculator on the test, absolutely. And so stat, regression, and then simple linear. So simple linear just means we have one X variable doing the predicting, and linear means we're going to fit a linear model to this. And then I select X, select Y. Got to do those two selections. That's all you got to do. And then go down and hit compute. And you get everything you need to answer bunches of questions. Remember, another nickname for the Y variable is the dependent variable, because we think Y and the grades depend on X, the hours, at least in part. We get the least squares regression equation, the predicted Y grade, or the predicted grade, which is the predicted Y value, equals Y-intercept 33 point, I'll call it 8, plus a slope of 6 point, I'll call it 5, times X, which is hours. You get the correlation coefficient R, 0.92, R squared, the coefficient of determination, almost 0.85. Okay. Also down here on the right, the bottom, there's an arrow, and it shows you a picture of the scatter plot with the best fitting line drawn through the scatter plot. So would you say this is a strong or a weak relationship? Deetra, I will get to R squared in just a moment. Yes. Okay, the strongs are right. This is a strong pattern. Please try to remember, real life data is not going to be perfect, but these points going from lower left to upper right steadily follow kind of the same slope as we go. And when we draw a line through the points, none of them are terribly far away from the points. It's a pretty good fit. So I would say there is a strong pattern, positive and linear. And since it does look like there's a linear pattern, then R is a number that makes sense to interpret. 0.92 is close to +1, indicating indeed a strong positive linear relationship between X and Y. So again, all the output that you need is on this table of output right here. And let me move that away for a moment. And let's go back. So when we're calculating the least squares regression line, the predicted grade, Y hat, equals about 33.8 plus 6.5x, or hours. Right? Here we are again with another chance for you to put into words what the slope means. I don't want to completely steal all your practice tonight, but let me give you another 20 seconds to try to jot down a sentence to put into words what the slope tells us about how much we expect grades to change for every additional hour spent on the essay. Hint, hint. See if you can write down a sentence. And reveal. As hours increase by 1, grade is predicted to increase by 6.5 points. Now, some of you might like to put that sentence in the other order and say grade is predicted to increase by 6.5 points for every additional 1 hour spent on the essay. Okay. Okay, Grace, yeah, good shot at that there. Yeah, and you can say how much you expect the grades to increase, Grace, by putting in the amount of the slope. So that's good. Okay, great. Okay, so now R and R squared. So again, I've already kind of interpreted R, so I've stolen your thunder on that one. Now R squared's a little bit different. R squared has to do with, remember I said that another nickname for Y is the dependent variable because we think that Y depends at least in part on X. We think grades depend at least in part on the hours spent on the essay, but maybe X, the hours spent on the essay, doesn't completely explain the variation in grades. But that's what it's getting at. R squared, 0.845, tells us that about 84.5% of the variation in grades, that's Y, is explained by X. You know, and to be a little more precise, I like saying it that way. It's the percentage of variation in Y that's explained by X. Get it? Emphasis on explained by X. That way you can remember something that's a little silly, but you can remember it because of the alliteration. But read it in context. About 84.5% of the variation in grades is explained by the linear relationship with time spent. That just means we have a really good choice for X. It's a really helpful predictor variable. It's helping explain nearly 85% of the variation in grades. Wouldn't you love for a teacher to be able to tell you with one variable something that explains a lot of the variation in grades? And so we want that to be a high percentage. If it's not, like if I'd put something silly in there, like a student's height, I wouldn't expect R or R squared to be very high because I don't think height explains much of anything associated with grades. Okay, let's see who did. So somebody had asked me, so Deetra, did I help you there with the R squared? You wanted to know about that. Wonderful. Okay. All right. So lastly here on this screen, let's use this prediction equation to calculate the predicted grade, that would be Y hat, of a person who spent 5 hours on the essay. So using this model, X is hours spent, so we just put in 5 for X and run that through, 33.8 plus 6.5 times 5, right? See what you get, and maybe confirm that we have the same answer. Matthew's got it. Super. 66.3 it is. Anybody else want to chime in and confirm that? Because either Matthew and I did it wrong the same way, or we are right. Anybody else want to confirm? Wonderful. Thank you. All right, so there's 3 of us with the same answer. I think that's good. I'm confident we did that right. All right, let's keep moving. Think in your mind, if somebody asks you, what is extrapolation, if you remember what that is. Here's a hint. The prefix extra means outside of, like extraterrestrial is outside of Earth. So extrapolating, must mean something is out of bounds. Maybe that's a hint. Something's outside of the bounds, right? So maybe this brings back to mind making predictions with values of the X variable that are outside the range of the data used to create the model. That's what extrapolating is. You don't want to do this. We only know that over the range of the X variable here, hours going from about 0 up to 10, we only know that across that range of hours that the relationship to grade is linear. We don't know beyond that if the relationship continues to be linear, or if it shoots up higher, or if it levels off, or if it drops. We don't know. So if somebody says, predict the grade for somebody who spent 0 hours, that's okay, because X ranges from 0 to 10. Or predict grade for somebody who spent 10 hours, that's okay. Predict grade for somebody who spent 4.5 or 9 hours, that's fine too. It doesn't have to be a data value. But it's not okay to predict the grade of somebody who spent 15 hours, because 15 is outside the range of the X data used to create this model. That would be an extrapolation. We don't want to do that. We simply don't have a database foundation to do that. Okay. Any questions before we leave that chapter? We're going to move into the chapter 5 probability next. I think we covered this one pretty thoroughly. Again, it might be a little more faster than you're comfortable with, but the recording will be available. All right, thank you. All right, so let's take a look in probability here. And basically, ands and ors conditionals are independent, or certain events independent of one another. You'll see contingency table, data, cards, and dice. Might not be limited to these, but that's some of the traditional things that we all do in our courses. All right, so there are some basic formulas that you need to be familiar with. The first one here is the probability of A union B. We use the word or when it comes to union of two events. That means we join together, like a union, we join together. It's the probability of A plus the probability of B minus the probability of the intersection. We're not excluding the intersection, but you might remember that sometimes the intersection gets double counted. So the upside down U is for intersection. It means the word and. A and B both occur. A or B means at least one of the two events occurs, either A or B or both. A union B. The vertical line, this is another symbol, just like union and intersection. The vertical line means the word given. This is like there's a given condition. Like I tell you that event B has occurred. So the way I read this is I say the probability of A given that B has occurred. So this has a formula. It's easy to do on a contingency table, but it does have a formula in case there's not a table. And so you'll notice that it's the intersection of the two events divided by the given condition. The given condition becomes who it's out of. It becomes your denominator. All right. The probability of the whole sample space equals 1.0. That doesn't mean 1%. That means 100%. Okay. One of the things you want to be careful of is decimals versus percentages. Okay, so throughout this, probabilities technically are in decimal form, but a lot of times your authors put a box and they put a percent sign after it, which means you have to multiply that decimal by 100% and report it as a percentage. So pay attention to how you're asked to report your answers. Here's the definition for independent events. There's two ways to do this. One way is to say the probability of A and B both occurring. In other words, the intersection equals the product of the probabilities, probability of A times probability of B. The way my students are probably familiar with it is this second definition. The probability of A given B equals the probability of A. It simply means that, hey, shout out, given that B occurred, makes no difference, doesn't change the probability at all. Okay, one of the examples I like to use in class is it's like, hey, there's a party this weekend, 100% chance I'm going. That's the probability of A. And then you tell me, hey, so-and-so is going to be there. And I'll say, I don't care, 100%, I'm still going. Well, I didn't think you wanted to run into so-and-so. I don't care, I'm still going. Okay, so what that means is that my going and that other person being there are independent of one another. It doesn't matter to me. Now, if it did matter, then the probability that I'm going would change. And that would mean there's some association between A and B, some association between my going and that person showing up. Okay. All right, so Margaret, union again. Yeah, union means A or B or both occur. At least one of the two events has to occur. Kind of like if there's a job application and it says to be eligible for this job, you have to have your associate's degree. You have to have 2 years of relevant experience. That means you got to have one or the other or both, right, Margaret? Yeah. And is the upside down one, and that means both, right? Now, so if the job application says to be eligible for this job, you have to have your 2-year degree and two years of experience. That means you've got to have both. Okay, so very good to clarify. The last formula here in the Chapter 5 probability list here is for complements of events. So basically the idea is that any event you name either occurs or it does not occur. Like tonight, it's either going to rain or it's not going to rain. Okay. I'm going to reach in the bag of M&Ms and pull out a red one, or I'm going to pull out one that is not red. The key word with complements is the word not. And since either event is surely going to occur or not occur, the sum of their probabilities always adds up to 1. So a complement, the probability of a complement is just 1 minus the probability of A. Like if the probability of rain is 30%, the probability of no rain is 1 minus 30%. Or 0.70, 70%. Okay. So complements. S is the sample space. That's right. Yep. Okay. All right. So here's a little bit of less practice. All right. Okay. So here's a contingency table. This is a typical setup that you can ask a lot of questions. I'm going to see if I can figure out how to write on this screen here. If not, I'll have to bring in my little whiteboard again, but let's see what we can do. So down the left side, we've got male, female, and total. Across the top, we've got car, truck, SUV, van, other, and total. And so we've got the total number of males, the total number of females, the total who have a car, the total who have a truck, the total who have SUV, total who have a van, total who have other. And then we've got the grand total of 200 people. So in all of these problems, one person is going to be randomly selected. Some typical things you need to be able to do are find the probability of one of the events that's named, like the probability of a female being selected, or the probability I select somebody who drives an SUV. Part C is going to be the probability that the person I select is female or drives a truck. D is going to be the probability I select somebody who is male and drives a van. Okay. And then they get a little bit different at the bottom of the page. So let's take a minute. And I think the easiest way to answer to keep us moving is just with unreduced fractions until we absolutely need to do some decimal comparisons. So if I randomly pick a person from this table, let's see what is the probability that the person I select is female. So just make a fraction, and thanks, Arden. Yeah, report an unreduced fraction. Yeah. Yeah. Oh, good. I can get a pen. Yeah. So there's 88 female, so there's 88 chances. Sorry for the errant line. I don't know where that came from. Okay, there's 88 chances out of 100, out of 200. 88 out of 200. Oh yeah, y'all got that. Um, very interesting how that happened. Give me a minute. I'm ooh, a little slow with how this writing goes here inside PowerPoint, but it's working. Yeah, 88 over 200. Good. You can worry about reducing the fraction. All right. Let's keep looking. How about the probability that the person I select drives an SUV? There you go. Answers are already popping in. It seems that these are pretty easy for you. I'm glad. Oops. Oh, it's not liking doing more than one thing at a time. Well, that's sad. I think to have to erase every time I shouldn't have to. There it goes. Yeah, you're going to be buzzing along quicker than I can at this rate, but we'll muddle through. Yeah, there's 53 who drive an SUV out of 200, so there's 53 out of 200 chances that one of them will be selected. Now this next one has an or in it, and if you remember the formula, this one might take you another minute, but remember it means one or the other or both events occur. So this is probability of female plus, oh, there it goes again, probability of truck minus probability of female and truck. All right. So look what happens. So we've got female, that's 88. Over 200. So we've used that entire row plus probability the person drives a truck. And there's 17 people who drive a truck. Now what happened when I use the 88 for this second row and when I use this column for truck, what happens? The people in the intersection got counted twice. They were a part of the 17 and they were part of the 88, but they only exist once. I can't count them twice. I need to subtract out the intersection. I'm not excluding them. Okay, I'm just correcting the double count. So 88 plus 17 minus 3, that's 88 plus 14, right? What do we get? Y'all are telling me you're already on to it. Yeah, Elisa, 102. That's right. Out of 200. Whoops, I'm so sorry for those little vertical lines. I don't know what happens. Yeah, so okay, I got you. Okay, we're all good. Okay, any questions on that one? That one tends to be one of the most missed kind of questions. Oh, and thank you, Arden, for converting that to a percentage. Okay, great. All right, let's do an and. And is just the intersection. So where is it that male and van intersect? That's right. 21 out of 200. Notice all of these have been out of 200, right? Okay, very good. All right. Now, look at the wording in number 2 here. This is a little different. This one says, find the probability that a randomly selected male, right? This isn't just a randomly selected person. This time, it's like I'm shouting out saying, hey, I selected a male. So what's the probability a randomly selected male drives a car? So now you know it's one of the male, right? It's one of the males. So how many is it out of? Right, it's out of 112. Okay. So this is there it goes again. Okay, so it's out of 112. And out of those 112, let's see, there are 34 who drive a car. Really sorry about these little intermittent vertical lines. I can't seem to control what's happening there. Okay. Okay. Questions on that one? Randomly selected male. You know it's one of the males, so it's out of the 112. Then you only look among that row. 34 of them drive a car. So 34 chances out of only the 112. Okay, good answering up in the chat. That's looking good. Number 3, find the probability that find the probability a randomly selected person who drives a car is male. So now it's a randomly selected person who drives a car. I gotta erase this, it's driving me crazy. So randomly selected person who drives a car. So that's the given condition this time, right? So this time we know that the person drives a car. And you're absolutely right. There's 71 people who drive a car. So it's only out of the people who drive a car. And among them, 34 are male. So notice these two problems, the numerator is the same because it's the intersection between the same two variables, driving a car and being. Just like Tennessee and Monroe streets, it's the same intersection as Monroe and Tennessee streets. It's the same spot. But what's different is who I tell you it's out of. In number 2, you know I selected a male. In number 3, you know I selected someone who drives a car. All right, you guys. That's a busy little page, wasn't it? All right, ready to move on? We better. Okay. Again, the idea of independent and mutually exclusive events kind of almost wraps us up here. 2 more screens here and then chapter 6. So if you're asked to find if 2 events are independent, you need to focus on one of these 2 definitions. And it depends on your teacher which one you use the most. Remember, if 2 events are independent, then the probability of A is not going to change, even if you know that B occurred. So this first definition, given that B occurred, does the probability of A still equal the probability of A when you don't know if B occurred? Well, if knowing that B occurred doesn't change the probability of A, then you say the events are independent. But if knowing that B occurred does change the probability of A, then you're going to say there must be some association there. They're not independent. So, your book gives these drop-down menus, and you have to match the pair. And so I'm going to take the first event given here, which is driving a truck. Probability truck. And I'm going to say that is 17 over 200. Now, Arden, we really are going to need the decimals this time, so thanks for providing those. And I'm going to compare that to the probability of driving a truck, given that the person I select is female. Okay, just make sure that the same event is up front. Okay, because that's what you want to compare. And so let's see, the probability the person drives a truck, given I pick a female. Focus in on given that I pick a female. Given that I pick a female, it's one of these 88 females. So out of those 88 females, only 3 drive a truck. Right, Matthew. All right. Now, if you can't look at 17 over 200 and 3 over 88 and tell if they're equal or not, then just go ahead and get some decimal equivalents and let's see what we get. So 17 out of 200 and 3 out of 88. So let's see, 17 out of 200. It's 0.085. Right, 8.5%. Thank you, Arden. And 3 out of 88. Matthew, thanks. 0.034, which is 3.4%. 0.034. Whoops, that goes again. Okay, so these are not equal. All right, these are not equal. So we say they are not independent. They're not independent, all right? If you'll allow me to abbreviate here. These are not independent, okay? Because knowing that I chose only among the females changed the probability of picking a truck driver. Can you do it any other way? Margaret, so there is this other definition here. And some of your teachers might have used it. Okay, so let me just separate the two. So A and B, this is just where A intersects B. So that would be the probability of somebody who drives a truck and or intersect. Mercy. Intersect with female. All right, and so where those two intersect, truck and female intersect on the table at 3 over 200. And we want to use this formula and compare and see if these are equal, question mark, to probability of truck times probability of female. All right, so probability of truck. So there's 17 out of 200 who drive a truck times female. There's 88 out of 200 who are female. So doing it this way, I've got another multiplication to do. And so if we all just take a minute and do that how we like. Over here, I get 0.0374 and 3 over 200 is 0.015. These are not equal. So I come to the same conclusion, Margaret, but I came to it a different way. Do you like one or the other of those? Can you handle one or the other of those? The second? Yeah, you like the second better. Cool. All righty then. That'll work. You can do it either way. All right. The other definition here on this page is are two events mutually exclusive? Mutually exclusive means they do not occur together. This is your old Venn diagrams where the two circles don't overlap. They're separate from each other. Okay. So when I look at van and car, these are mutually exclusive because you know, van is over here, and car is over here, and they're completely separate. There's those who drive a car and there's those who drive a van. They do not intersect. And so I'd say yes, these are yes. Because there's no overlap. They do not overlap. They do not intersect. No intersection. All right. And so I could say that van intersect car is a null set or an empty set. They don't intersect. An example of mutually exclusive. Well, this is an example of mutually exclusive because car and van don't intersect. Another one would be what if I had, let me just change color here. What if I go over here to where the where it says SUV? I'm going to circle SUV and male, and let's suppose that there's a 0 here for a minute. Then I could say that SUV and male are mutually exclusive, Deetra, because then there would be nobody in the intersection. How about that? That's another way you can have mutually exclusive events. If there's nobody in the intersection, they're mutually exclusive. They don't occur together. They don't overlap. Is that better? Cool. All right. All right, so we need to keep moving. So the last screen I have here in the chapter 5 is there is a 2% chance of a 7.5 magnitude earthquake or larger in San Francisco during any given year. Assuming independence, what's the probability San Francisco has an earthquake of this magnitude in each of the next 4 years? So if your teacher went over the multiplication rule, then this is something that you will be ready to answer. I did not go this into this material with my students. Oh, Miriam wants to go back a second. Miriam, so what would it look like if it wasn't mutually exclusive? Well, all these others. I mean, look at car and male. Look where car intersects male. There's 34 people there. So those are not mutually exclusive. They overlap. There's some people who both are male and drive a car. They do occur together. So they're not mutually exclusive. Okay, so when there's numbers in the cell and you look at where the column and the row intersect and there's numbers there other than 0, that's not mutually exclusive. They occur together. There's people who have both those characteristics. Miriam, is that better? Okay, cool. All right. So all right, so let's just take a look here about so when you have events that are independent, remember that A and B is the product of the two probabilities, probability A times probability B. We just did a problem that looked like that. And so, hold up here. All right. And so, if I want to know over the next 4 years, so if there's a 2% chance of having an earthquake and they want to know what's the probability they have an earthquake over the next, in each of the next 4 years? That means 0.02 for the first year times 0.02 for the second year times 0.02 for the third year times 0.02 for the fourth year. So this is 0.02. Whoa, can't stand it. Raised to the fourth power. So let's see what we get. 0.02 raised to the fourth power, which again is 0.02 times 0.02 times 0.02 times 0.02. So this is very small. This is 0.00 4 6, and in the 7th decimal place I've got a 1 and then a 6. Okay. Hi Margaret. It's for students in my face-to-face class. I did not cover that, so it will not be on my face-to-face class test, I don't believe. If you had it in your homework, I guess you better be ready for it, but I don't remember going over it in class. So if it was in your homework, be ready for it. Right. So this is the probability that there'll be an earthquake in each of the next 4 years. The next one is, what's the probability that there will not be an earthquake in each of the next 4 years? So at this point, we want to make use of complementary events. And I just lost my little pointer. Where is it? There it is. It's so small I can't see it. Okay, so if the probability that there is an earthquake in a given year is 0.02, with the use of complements, what's the probability there's not an earthquake in a given year? You can tell me that in the chat box. If there's a probability, a 2% chance of an earthquake, what's the probability there won't be an earthquake? Thank you for your message, Jonathan. I understand.
They will have the recording by tomorrow.
Thank you.
Thank you.
Okay. So let's see, one question at a time. If there's a 2% chance of an earthquake in a given year, what's the probability there's not an earthquake in a given year? Nobody's ready to answer that one? Well, let me put it to you this way. If the probability of rain tomorrow is 2%, what's the probability there's no rain tomorrow? Yeah, Gabrielle, 98%. Yeah, that's right. And so in the next year, the probability there's no rain, I mean there's no earthquake is 0.98. And let's see, Deetra, this will probably answer your question. And then if each year is independent of each other year, the probability that there's no earthquake the next year is also 0.98. So that'd be 0.98 times 0.98 would be 0.98 squared times, if the years are independent, the probability there's no earthquake in the third year is 0.98. So that would be 0.98 cubed. And then for the fourth year, 0.98 again. So now I'm up to having 0.98 to the fourth power. Okay, so when we multiply something by itself a number of times, it's the same as raising it to the power. So yeah, so let's see. Deidre, did I answer that question about powers well enough? Arden, thank you, Deidre. Arden, I got a different answer. 0.98 to the fourth power, I got 0.92 rounded. 0.92 rounded. Can you check your work on that? Okay. Let me know if that turns out for you or not. Okay, so I'm going to keep moving here. Now, the title of this slide says all, at least one, and none. Arden wants to know how I got 0.98. It's just 1 minus 0.02. So again, Arden, if the chance of an earthquake any given year is 2%, then the chance there's not an earthquake any given year is its complement, 0.98. Okay, just like if the probability of rain tomorrow is 2%, the probability of no rain tomorrow is 98%. Yeah, good. All right. Okay, now think about this. Okay, I've got some pens in my hand. These are all of my pens. All right, 3 of them. Now I'm going to hide this away from you. I'm going to tell you that something dropped on the floor. And if I tell you that that none of the pens dropped on the floor, then I still have all 3 pens. But what's the probability at least one pen dropped on the floor? That's the probability that one or more of them dropped on the floor, right? If you think about none and at least one, they're complements. If you think about reaching in a bag of M&Ms and pulling out an M&M, it could be that at least one of them, or maybe I grab a handful of them. That's probably what I'm more likely to do. I'm going to grab a handful of M&Ms out of the bag. Could be that at least one of them is red. At least one of them is red. Or it could be that none of them are red. Okay. So another situation. I reach in my pocket. If I don't have at least one coin in my pocket, I got none. Need you to think about the relationship between none and at least one to make this last question here easy. So sorry about this ink thing. It's just, I'm going to see if it does the same thing when I use the stylus instead of the mouse. Let me go back and give it a try. It won't even let me write with the stylus in here. Don't know why, guys. I'll just muddle through. So none And at least one are complements. None and at least one are complements. So that means that the probability of none plus the probability of at least one adds up to 1.0. That's what the definition of complements says. The probability of A plus the probability A complement equals 1. So I want the probability that San Francisco has at least one earthquake in the next 4 years. Now that's kind of a hard thing to figure out. But it's real easy to take 1 minus the probability of none, because we already figured out that one. And that would give me the probability of at least 1. So that would be 1.0 minus 0.92. And that will give me the 0.08 that I'm looking for. Okay, so this is what I'm looking for. Let that sink in for a minute. I think of all the scenarios I gave you, probably the coin in the pocket's the easiest one to understand. I either have at least one coin or I've got none. We got March Madness coming up. Send me to the foul line. I make at least one shot or I don't make any. Okay, one of those has to be true. So they have to, the probabilities of an event and its complement have to add up to 1.0, which means algebraically then 1 minus the probability of the event, you know, like none, equals the probability of its complement, like at least 1. That one might take a little bit more time to sink in, but there you go. You can replay the video later. Okay. All right. We've got 7:38. All right. Let's see if we can wrap up with chapter 6 now. We're going to focus on the normal distribution in chapter 6 tonight. I know my students, we covered some things in 6.1 on discrete random variables. Those are not among the slides tonight, but I've got my regular office hour coming up at 8 o'clock after this review. So if anybody wants to stick around, I can do something else. I think I might have an appointment with somebody. If that person comes in and identifies themselves, I might need to have a little private time, but and I think somebody's going to do the same at 8:30. But if you have another quick question or two, maybe I can still answer. All right. So remember the normal distribution that, it's bell-shaped, it's symmetric. The total area under the curve is 1.0, which represents probability. Everything you learned about the empirical rule is still true, that if you go plus minus 1 standard deviation, you've got about 68% of the data. If you go plus minus 2 standard deviations from the mean, you've got about 95% of the data. If you go 3 standard deviations, you've got almost all, about 99.7% of the data. Okay. If anybody starts talking about the standard normal distribution, that's the scale of Z. That means the mean is 0 and the standard deviation is 1. And that's going to come into play in some problems here in just a minute. So sometimes we're calculating probabilities for given values of X or Z. And sometimes we're calculating values of X or Z for given probabilities. Right? So there's a skill set there. All right, let's describe the following as either discrete or continuous. Random variables. Okay, so speaking of the number of coins somebody has in their pocket, this is something that we count, right? So what kind of variable would that be? D for discrete or C for continuous? Yep, here come all the D's for discrete. You are correct. All right, number of cats in the neighborhood. Probably more of them, but it's still something you count, right? It's not something you measure, it's something you count. So again, yep, you're right, it's discrete. And what about time? Do we count time or do we measure time? So yeah, time, there we go. Here's some C's for continuous. You're right. Time is on a continuum. That's right. Good. And cholesterol levels. Do we count them or measure them? If you're typing C's, keep on doing so. These are measured. Right, these are measured. Okay. Yeah, I like to tell my students that if you think about a number line and you think about values of the variable, if you have to jump from one possible value to the next, it would be discrete. But if on your number line, there's any number of values that are possible in between, that would be continuous. One of the examples I like to give is somebody's shoe size is discrete. You can go to the store, you can get a 6, a 6.5, a 7, a 7.5. Larger shoe sizes, 12, 12.5, 13, 13.5. You can't get an 11.62 or a 9.18 shoe size. Sorry. That might be the length of your foot, but you're not going to get that in a shoe size. Length of your foot is continuous, right? It doesn't mean your foot goes on and on forever. That's not what continuous means in this case. Continuous means the scale doesn't have any breaks in it in between possible values of the variable. Any values possible for the length of somebody's foot. Somebody's foot could be any length. But the shoe sizes that are out there available, they're whole and half sizes. All right, here we go. Some of the typical kinds of problems we do here are normal distribution problems. Again, we're going to pull in StatCrunch to help us with these calculations. But notice that every single one of the problems on this page says find the probability, find the probability, find the probability. It could also be worded as find the proportion or find the percentage, because area under the curve represents probability, because a certain percentage of the distribution is in a certain region of interest. So let's read this one. Circumferences of regulation soccer balls have a mean of 69 centimeters and a standard deviation of 1.5 centimeters. Assume the circumferences of the soccer balls are normally distributed. So we can say that X is normally distributed with a mean, that's letter mu, Greek letter mu, 69. And little sigma, that's standard deviation, equal to 1.5. And we're just going to know that this is in centimeters. All right, so if I want the probability that a randomly selected soccer ball has a circumference greater than 71, this is going to be the probability that X is greater than 71. Capital N means normal. And the little squiggly line means has the distribution. So that means that X has a normal distribution. That means it has this bell shape that follows the empirical rule percentages. it means that the mean is centered at 69. And if I want the probability that a randomly selected soccer ball has a circumference greater than 71, well, that's going to be over here. And greater than means I want the area under the curve to the right of 71. Okay, is that clear? All right, so I'm going to pull StatCrunch over again. And I'm going to show you the stat calculator. So we're going to pull down the stat menu and go to calculator, and then the submenu normal distribution. So take a look at that pathway. Stat, calculators, submenu normal. And I have a mean of 69. I have a standard deviation of 1.5. So I have to enter those. I want to flip the inequality sign to point to the right because I want greater than, pointing to the right, greater than 71. So that's all there is to it. All right. This is a given value of the variable circumference. Compute, and it draws a little picture kind of like mine. Mine's taller and skinnier. There's a shorter and wider. Doesn't matter. But the area under the curve to the right of 71 reflects the probability. So I'm going to just call this 0.0912. And I'll pull that screen back in just a minute. 0.0912. Did mine. .0912. Okay, so that is the area under the curve to the right of 71. Let's look at the next one. This is the probability a randomly selected soccer ball has a circumference less than. So this would be X, the circumference is less than 68. All right. So when I think about representing this, again, the mean is at 69. So 68 is pretty close by here. Sorry about that. Whoa. And fortunately, I do want to shade in all of this to the left of 68 so I can cover up the weird thing that's going on. All right. So this time I'm going to the left of or less than 68. So I'll pull this back in. I'm going to start this over from scratch in case you missed it last time. I'm going to go to the stat pull down menu, the calculators, and then to normal distribution. And again, my mean is 69. My standard deviation is 1.5. And less than points to the left. So less than 68. Okay. And hit compute. So it draws a picture a little prettier than mine. And the area to the left of 68 is the probability a randomly selected ball has a circumference less than 68 centimeters, which is 0.25, I'll say 0.2525. 0.2525. Okay. Any problems yet? Right. Okay, let's see. Next one. This time we want the probability that randomly selected soccer ball has circumference between 62 and 67. So again, 69 is the mean. 62 would be further down. And 67 would also be to the left of the mean. So there's this little sliver in here that I want the area of. Now, the way that that looks when you write a probability statement, this would be the probability that X is sitting in between the two numbers. 62 over here on the left, and 67 over here on the right, with the inequality signs in between like that. This is what we call a between problem, because X is between two values, 62 and 67. So in StatCrunch, there's a special button we need to press for it to do the between buttons. So far, we've only done a greater than and a less than, all right? So, but now we're going to do a between problem. So let me pull it back over between 62 and 67. So see, with the standard button here depressed, we only get the idea, the option to do less thans or greater thans in that statement at the bottom. But if I come up here and I hit the between button, then it's depressed. And now I can put in two values, a 62 on the left of X and a 67 on the right of X. How nice is that, right? And then hit compute. And now it looks like it shaded a left tail area, but that's just because 62 is further down the chart than I drew it on mine. And so it doesn't look quite the same, but I promise you that's right. This is 0.0912. 0.0912. Right. Any questions on that one? All right, y'all hanging in there real good with me. Thank you. I think we've just got a couple of screens left, and let's see what's on there. All right. Says on a busy day, the average roller coaster wait time at a large amusement park is 27 minutes. Suppose the standard deviation of wait times is 11.9 minutes, and the distribution of wait times is approximately normally distributed. To improve customer satisfaction, the amusement park manager has decided to give food coupons to customers with long wait times. The manager decides to give coupons to the top 10% of people waiting the longest. What's the minimum wait time for the top 10%? So this time they're asking you for a value of the variable, and they gave you the percentage, didn't they? All right. So in a picture, what's going on here is that the average wait time is 27 minutes. Yeah, maybe I want to write that down somewhere, that mu is 27 minutes. That's the mean, and the standard deviation is 11.9 minutes. All right, so 27 minutes, just the average. You might be waiting longer than that. And one standard deviation is already 12 minutes. All right, so somewhere over here is a cutoff time for the top 10%. So 10% written as a decimal to represent area or probability would be 0.10. So this time what we have is the probability that X, that's the waiting time, is greater than some value I don't know, is 0.10. Take a good look at this. This problem is different because we don't know the value of the variable on the number line that cuts off the top 10%, but we do know the area under the curve. The probability is 0.10. Writing it this way, drawing a picture, can help you set it up correctly so when you get into StatCrunch, you know exactly what to put where. So let me bring over StatCrunch. We've got a new mean and standard deviation. This is a new problem. Roller coaster wait time, average is 27 minutes. Standard deviation 11.9. And this is not a between problem. This is a greater than problem. So I hit the standard button. I make the arrow point to the right for greater than. I don't know what the number is, blank it out. But I do know the upper tail area is 0.10. So that's the setup. Take a good look at it. That's the setup in StatCrunch. Okay, when I hit compute, it tells me that that wait time is going to be for the upper 10%. The ones who are going to get coupons for food, they waited a little bit more than 42 minutes. All right, 42.25 minutes. 42.25. Whoops, sorry. 42.25. Okay, questions on that one? And this says, what is the z-score that corresponds to this time? Well, I would like to demonstrate the formula for z-score. So this is one way we can do that. You take a value, you subtract the mean, and you divide by the standard deviation. Somehow I just knew that was going to happen. Nice. All right. So I've got my value of x. It's 42.25. I'm going to subtract the mean of 27. I'm going to divide by the standard deviation of 11.9. All right, when you're doing this problem, whether you're using a graphing calculator, a little scientific calculator, a basic calculator, whatever, you're using, make sure you get the numerator done first. So 42.25 minus 27 equals, then divide by 11.9. Make sure you get the order of operations going correctly for yourself. This ought to be 1.28. Okay. Questions on that screen? We got one more to go. Okay. Oh, I lied. There were two. Huh. For sure, we were almost done. Okay, but that's okay. So standard normal. The only thing different here is we're on the z-scale. Z-scores, remember, they count the number of standard deviations above or below the mean you are. So the mean is always 0. And the standard deviation is always 1. Okay, so the mean is always 0. The standard deviation is always 1. So it's normal with this particular mean and this particular standard deviation. Okay. So on the left here, I've got a probability problem. Find the probability z is less than negative 1.35. And then another one, the probability z is greater than 2.1. So StatCrunch can help with both of these. You just have to remember if standard normal is mentioned, that you do know the mean and standard deviation are 0 and 1. Okay, so let's see. I want to do mean of 0, standard deviation of 1. I want to flip the sign around to go less than negative 1.35. Hit compute, and it draws a nice little picture. Tells me the area under the curve to the left of negative 1.35 is 0.0885. 0.0885. Is 0.0885. All right. Okay, somehow I managed to really disappear my stat crunch. Give me just a minute. Let's open up. Here it is. Okay. All right. The next one is I want to flip this around and go greater than 2.1. This is going to be 0.01. I'll round up 79. 0.179. Okay. So same thing we've been doing, only on the Z scale. Any questions on that screen? All right. I should have said on that half of the screen, because over here I've got something else. Find the Z-score corresponding to the shaded area. So this time I give you the area and you find what the Z-score is. All right. So remember, this is, this is where we've got the probability that Z is less than something equals 0.2546. It's just, I don't know what the something is. Okay. But the area under the curve, that goes over here on the right side of the equation. So let's bring in stat crunch and say, well, I'm on the Z scale, so the mean and standard deviation are 0 and 1. The probability that the variable is less than something is, that means equals 0.2546. So you just leave that value of the variable blank. That's what we're trying to find out. And it tells us that that would be about negative 0.66. Negative 0.66. Questions on that one? All right. Let's see here then. So this next one here is the probability that Z is greater than something is 0.1075. Don't know what that value is. That's what I'm going to find out. I'll bring in stat crunch. I'll flip the sign around. So we're pointing to the right for greater than. I don't know what the value is, but I know the area under the tail, the probability is 0.1075. Compute. And the z-score is going to round to 1.24. 1.24. Okay. All right. We're down to our last screen, and this has to do with the word percentile. Okay, the word percentile. All right. So it says, according to National Health Center, the heights of 6-year-old girls are normally distributed with a mean of 45, a standard deviation of 2. So the variable is height, the heights of 6-year-olds. It says, in which percentile is a girl who is 47.4 inches tall. So what you need to remember for me or for yourself is that all these tile words like quartile and percentile, that has to do with what percent of the data is below a certain value. So it's always referring to the less than side. So if I look at the heights of these girls, they're centered at a mean of 45, and they're telling us we've got somebody who is 47.4 inches tall. So we know the number on the number line. They want to know what percentile that is. That means they want to know the area under the curve. Really, all they're asking is, what is the probability that X is less than 47.4? If they want to know the percentile, they want to know what percent of the heights are less than that. And that will determine the percentile rank for that height. So pay attention to what's given. If the point on the number line is given, then you put it here in the probability statement and how X relates to it, less than, greater than, whatever. So we'll bring in StatCrunch and we'll put in a new mean, 45, and a new standard deviation, 2, and flip this around to represent less than 47.4. Less than 47.4. And the area under the curve to the left of that is 0.8849. 0.8849. Now I'm going to convert that 0.8849 on. So first of all, decimal form, 0.8849. But if they want to know what percentile that is, I'm going to multiply by 100%. That's going to be the 88.49. That's crazy. Percentile. Usually people speak about percentiles in whole numbers, like that's somewhere between the 88th percentile and the 89th percentile. That means that about 88.5% of the heights are less than that height. Percentile always has to do with the percent of data less than, to the left of a certain value. And our last problem tonight says, if the 6-year-old girl who is 47.4 inches tall grows up to be a woman at the same percentile, what height will she be? So this one doesn't say, find me the percentage. It says, what height will she be? So now what we're talking about is we've got the new distribution for the women. And they tell me that the women have a mean of 64. They're grown up, they're tall, and a standard deviation of 2.5. But this person's going to grow up to have the same percentile as before. So this area is going to be 0.8849. And we want to know how tall she grows up to be. So we have to find a value of the variable. So this is going to be the probability that X is less than some number is 0.8849. But we need to be careful that we've got a new mean and standard deviation for for the adult women. I'll bring in StatCrunch one more time. And I'm going to put in the new mean for the adult women, 64. Standard deviation, 2.5. Probability X is less than some number is 0.8849. And that number is a height of 66.999. That's about 67 inches. I'm going to call it 67 inches. Whoops, you'd know it. The last thing I have to write. 67 inches. Okay. And that's how you do this. All right. So that's quite the grand tour. And so the recommendation is now that you reflect on how you did on this and where you need to improve, and get with your own teachers as to what you might be struggling with before your test comes up. I hope that this has been helpful, and I know that I've got a student coming in for an 8:30 appointment, but I'm going to stop the recording now, and if anybody wants to hang out, feel free, and I'll try to help you out. So let me find the recording button to stop it here.